Some say tomato, some say tomato. We say lycopene cyclizes to beta-carotene. Les Pommes D'amour, or the apples of love, is a phrase used to describe tomatoes in French. We became interested in lycopene, a compound found in tomatoes that not only gives it its red color, but as a precursor to alpha and beta-carotene, the organic chemistry behind the formation. Lycopene is a planar 40 carbon atom molecule that has 11 conjugated pi bonds that all exist in the transformation. Since we're dealing with a hydrocarbon compound, ionization states do not come into play. The pathways in which lycopene cyclizes into either alpha or beta-carotene are mediated by a cyclase enzyme. The two cyclases, epsilon and beta, act on the molecule to form rings on each end of the lycopene, forming a carotenoid structure. Through cyclization, the number of conjugated pi bonds can differ in the carotenoid products. While beta-carotene maintains the 11 conjugated pi bond system, alpha-carotene is altered to contain only 10 conjugated pi bonds.
In this slide, we see the particular pathways lycopene goes through in order to cyclize into either alpha or beta-carotene. Lycopene initially forms the intermediate gamma-carotene as a result of beta-cyclase enzymatic activity. It is important to note that the ends of lycopene cyclize independent of each other, meaning that only one end is cyclized at a time. The mechanism we are showing after this shows simultaneous cyclization because the cyclase enzyme has no preference to which end is cyclized first.
First, we will explore the mechanism of alpha-carotene synthesis. In box 1, it is hypothesized that the terminal pi bonds on both sides of lycopene grab a hydrogen atom from a charged amino acid residue in the cyclase's active site, in a classic association of an electrophile with a pi bond, to form tertiary carbocations at the positions labeled 1. In box 2, the double bond between carbons 5 and 6 attack the tertiary carbocations at position 1, in an intramolecular association of an electrophile with a pi bond. This forms 6-membered rings on both ends of lycopene, with carbocations formed at position 5. In box 3, the hydrogen atom dissociates at positions 4 on the left ring and position 6 on the right ring to both form double bonds in a dissociation of the electrophile step. Through our FMO analysis, we see that this is a sigma to A pi-type interaction because we form new double bonds in our products. Now, moving on to the second possible product, and potentially the more energetically favored product of the synthesis of beta-carotene. In box 1, just like the synthesis of alpha-carotene, the terminal pi bonds grab a hydrogen atom from a charged amino acid residue in the cyclase's active site. In a classic association of an electrophile to a pi bond. The carbocations, therefore, are formed just like in alpha-carotene on the positions labeled 1. In box 2, the double bond connecting carbons 5 and 6 on both sides attack the carbocation at position 1 in an intramolecular association of an electrophile to a pi bond. This forms 6-membered rings on both sides of the molecule, with a tertiary carbocation formed at position 5. In box 3, this is really the key difference between alpha and beta-carotene. In this step, the hydrogen atom connected to carbon 6 dissociates, donating its electron density to the carbocation's atom-centered orbital at position 5, forming a double bond between carbons 5 and 6. In contrast, alpha-carotene had a hydrogen atom dissociate from carbon 4, forming a double bond between carbons 4 and 5. Since beta-carotene has its double bond between carbons 5 and 6, it is continuous with the rest of the conjugated pi system. We hypothesize that the preference of beta-carotene over alpha-carotene is due to the stability that beta-carotene offers through the additional conjugated pi bond. In this case, it would make sense that beta-carotene would be the thermodynamic product, thus the favored product, and alpha-carotene the kinetic product, But although we are dealing with enzymes that have not properly been studied, our research does not elucidate any conclusive statements.
To conclude, although the exact crystal structure of cyclase enzyme has not been determined, scientists have been researching it in depth. It is clear to us now why beta-carotene is favored and how it is formed. Hopefully, we will soon learn the exact residues of cyclase that cause proton removal and the different ring products. Knowing these facts could help us use lycopene as an antioxidant and possibly use it in cancer prevention.